Hi everybody. This time I think I can really give you a short video. I just want to show you how to use Mathematica to solve linear programming problems. This should not take long. So I actually wrote a couple convenience functions for you to use, and I've uploaded this file to the modules page. The way you'd use it is you'd open this file and then you'd go to the evaluation menu and select evaluate initialization cells. It'll read in these two commands so they'll be available to you for any further work you might do. Mathematica has a built-in command for doing linear programming. It's called linear programming. By the way, one useful feature, I don't know if I've mentioned this, but if you just mouse over a Mathematica command, you'll see you get a little menu pops up. If you click on the eye, you'll get the information window, right, and it'll tell you how the function works and what the arguments mean and everything like that. So the programming function, it takes three arguments. It takes the objective vector, it takes the matrix, which we call A, and then it takes the constants that you're comparing m times x to, right? So the way they describe this, it says linear programming c comma m comma b finds a vector x that minimizes the quantity c dot x subject to the constraints that mx is greater than or equal to b and x is non-negative, right? So all the entries in x are non-negative. So basically, linear programming solves the minimization problem, right? It finds a vector which, when dotted with c, attains a minimum value subject to the constraints that m times x is greater than or equal to b, and x has to be non-negative. So as I said, I wrote two convenience functions. I have a bad memory myself. I tend to forget whether linear programming solves the minimization problem or the maximization problem and silly stuff like that. So I wrote two functions, a min LP and a max LP, that just do each one so it's easy to remember. And it also it returns the actual value of the objective function, so it returns the optimum value of the objective function. So the way it works is like this. So here's an example here. So suppose you have an A matrix, which is 2010, 510, 1510, right? So this would actually be a 3x2 matrix, right? And then you've got a two-dimensional B vector and a three-dimensional C vector, okay? And then suppose the problem is you're trying to find a two-dimensional vector x such that x dotted with b is minimized, subject to the constraint that x has to be non-negative and A times x, this A matrix times x, has to be greater than or equal to c. Okay, so you can just run this command, min LP bvec amat cvec. So the first entry is the objective vector, the second is the matrix, and the third entry is the vector of constants, right? In this case, that A times x has to be greater than or equal to these constants. Okay, so you enter it, and we get our answer. This says that the optimal x vector is 3 comma 13 halves, and the actual value of the optimal value of the objective function is 600 in that case. Okay, and then if you want to solve a max problem, you can do it using the max LP. So here we find the max LP of a problem where you're trying to find, let's say, a vector y, which when dotted times the c vector is maximal, subject to the constraint that the transpose of the AMAT is less than or equal to the b vector. The transpose of the AMAT times this vector y is less than or equal to the b vector, right? And so you get that. This one happens to have the same answer. How do you like that? Or at least the same value for the objective function. I can talk more about this in office hours if you're still confused, but it should be pretty straightforward and very fast.